Hey, welcome to this quick update of OpenBMC running on ProLiant Gen11 platform. So we'll be focusing today on discussing about booting the BMC from the network. So there are some very strong advantages of doing that. The first one is to get rid of the local storage capacity, which is limited and fixed to a couple of megabytes. The other one might be to use a read-write file systems and trashing the compression algorithm used when using the SPI storage. And the last one will be around expanding the file systems with a packet manager, and which would be benefiting the upgrade process of the BMC in the case some security threats appears or you want to enhance it. Instead of refreshing the whole systems, you will be just managing the whole OpenBMC image like standard operating systems from the host. So we build a quick proof of concept, and the main target to transfer the storage from a local storage to a network storage has been to set up an iSCSI environment. So the main benefit of iSCSI is that this is a block storage. This is pretty efficient. This is well known. It's rock solid, and it has proven to scale, especially with the expansion of the VMs and the cloud. And we were thinking that trying to build a BMC with iSCSI as a storage backup systems would be just fun, efficient, and probably very quick. So to do that, we need to put in place some infrastructures. The basic infrastructures that we have to initiate is a DHCP servers. So as you might be aware, I'm a big fan of Golang, and I digged a little bit about what was available on GitHub regarding Golang solution for DHCP, and I ended up to select the core DHCP project, which has been designed by some Meta engineers. And it has proven to be very flexible, and you can add some plugins to it. So the first things I have made is to create a plugins which will auto-configure some TFTP servers and iSCSI target when a new server is discovered on the network. So roughly the idea is the BMC is going to issue a DHCP request. So the server is going to receive that request and is going to process it. And when it is going to process it, if the client is not known to the subsystems, it will automatically allocate an OpenBMC image to that new client. And that OpenBMC image is going to be generic enough just to be able to boot the new servers and attach to local iSCSI storage, which will be also automatically configured. So everything is open source. You can get access to my GitHub repo. So I'm under the process to offer that code to the core DHCP team. And you can find the Discover plugin under the plugins directory, as you might be expecting. This is just to go source file. The main code is within the discover.go. It's copyrighted by Cal Enterprise, as I have done that work during my work time. And you will be seeing that it is configuring automatically a TGT, which is the iSCSI user space target environment from a Linux-based systems, and the TFTP servers when it is receiving some request. I have embedded into core DHCP a small HTTP server, so where you can have a look to the current clients which are available. So right now, for that demo purpose, it's not yet available because I didn't started it yet. But you might be expecting that small interface, and we will get back to it when we will be starting the services on the server side. So the second thing is to provide a Linux kernel. So for the one who are familiar with OpenBMC, the Linux kernel image is packed with an initram FS into a fit image, which is stored on the flash. So what I have done to create an iSCSI bootable environment is I changed the OpenBMC image generation by breaking down the MTD files into two files. So one of them is going to be roughly the feed image, which is going to contain the kernel and the init RAMFS, and that is going to be retrieved through TFTP booting the BMC. And the second one is the user space file system. So the user space file system in OpenBMC is using SquashFS extensively. In our cases with iSCSI, I'm switching to ext4, which is a very well-known file system under Linux. And and it is going to be way much bigger than with OpenBMC because SquashFS is using compression. So right now, by switching this from SquashFS to ext4, we are moving from a couple of megabytes to hundreds of megabytes and roughly 200 megabytes. Keep in mind that the advantages is that the BMC chip is pretty slow, so using compression requires time to run the I/O, and by moving to ext4, we gain the benefit of running with a read-write mode. So the TFTP server is going to be based also on Golang. And I tested everything by using GoTFTP D example, which is also available on GitHub. So when you are all set up, so you need to configure a small controller node, and we'll call it a controller node, which is going to run the TFTP environment and the iSCSI target servers as well as the core DHCP. So to configure the iSCSI target server, you just need to install TGT on your Linux-based operating system, and then you need to install core DHCP with the Discover plugin turned on and the GoTFTP server. So then you need to load the feed image into the TFTP boot. So you can see there that I have preloaded a feed image on my systems. It's roughly 6 megabytes, and you need to also have an iSCSI image for the user space environment, which is called iSCSI.tgt. In my case, it's roughly 210 megabytes, and you install it to the iSCSI target default file system, which is into /var/lib/iSCSI_disk in my cases. So when this is done, you need to start core DHCP, and this is going to listen to the various interfaces. And you can get back to your web browser and see that the core DHCP web services are started. And each time there is a DHCP request which is going to come in, it is going to create a default boot environment. So in my cases, I got a fake OpenBMC system running on my network, which is coming up with that specific MAC address. And we can see that an IP address has been allocated. It is set up as a new, so it means that the system is not attached to the iSCSI storage. And that small cross at the back is going to give you the opportunity to remove the configuration of that specific systems from the core DHCP environment. So when this is done, so we can start the client um, and stop the start during the U-boot process. So I'm going to do that right now. So my client is available just right here. We can see that the GXP bootloader is starting, the security is being checked, and the silicon root of trust is currently validating the U-boot image, and the U-boot is eventually going to start. We have to wait a little bit for that process to go through, and in the meantime, we can start the TFTP server. So the TFTP server is very basic and is going to offer content to the client. That is normal that you can see some requests coming up on the TFTP side. So the security has been validated. U-boot is currently ramping up. I stopped the boot, so I am on the prompt on U-boot. So the first thing is to set the load address of the upcoming feed image. So I'm going to overwrite U-boot and setting up that address in my case. The second step is to issue a DHCP request. So we'll be seeing the DHCP request coming into that window. and the DHCP request has been issued. So what you can see there is that a specific boot environment has been set up for the MAC address of my systems. So which means that the default boot image has been copied and has been set up for that specific client. So if I get back to the web interface, my client should be there. Yes, it is here. It is just right there, and it is set up as new. So you might be expecting to that the iSCSI environment has been set up. So we have successfully loaded the boot environment into the memory of the target systems, and we can start from memory. So by issuing the boot command. So this is going to validate the fit image, and it is going also to check the init ramfs and the kernel signatures. And if everything is okay, it is going to start and boot. So hopefully that will be the case. When the kernel is going to boot, it is going to run a specific init ramfs into which I'm initializing the network very early into the boot process. This is currently happening right now. So this UDHCP sending discover requests are there just to request a new TCP IP address. And then an iSCSI discover command is issued. So let's stop a little bit the boot and have a look to what's going on right there. So just after the DHCP request is issued, so a new IP is offered, and that IP is setting up a few things. So it is setting up the default DNS, which are in our cases the Google DNS, and then it is sending a target discovery. So that target discovery is coming with a random IQN, which is based on the new MAC address from the systems, and a specific target is available and is mounted as a SCSI devices. And that device, which is just right there, is 210 megabyte. As we have seen, this is coming from the default iSCSI disk image. And it's available as a read-write uh, file systems, and it is going to be mounted as SDFI systems. So as soon as it is mounted, it is used to discover the hardware configuration of the incoming systems. And as this is using a common OpenBMC image between whole generation of ProLiant systems for Gen11, it is using extensively GTS overlay to configure the subsystems. So what is happening right now is we have a unique ID per Gen11 systems. In our case, I'm currently using an RL300 for that demo. And this unique number is retrieved and is matched with various overlays, which are used to configure the OpenBMC image. So we can see that into that systems, there is a couple of iSCSI muxes which are needed to be configured. There are some PCI double EEPROM which are available, some UBMs also which are available on these machines, a couple of PSUs, and some LED. All of that is happening dynamically, and this is used to configure the systems. So some iSCSI devices might not be available during the boot of the OpenBMC image. The main reason behind that is the host is currently turned off. So when down, so the system is going to fully boot and is going to be available through the web. So we can get back to core DHCP and we should be able to see that our system has been booted and it's connected to the iSCSI target. So we cannot scrap it because as long as it is connected, it means that the client is currently issuing command to the iSCSI target. When we are going to shut down the client, the state is going to switch back to new, and you can remove the client from the systems. So OpenBMC is booted, and we can connect to it. Let's have a look to a few things. Um, So when we issue an LSBLK, we can see that there is the SDS subsystem which is mounted there, and the SDS subsystem is our iSCSI target. So that is a great news. And when we run the df, the /5 systems is definitely the iSCSI target. So what is great also is that this is read-write. So if I go to USL builds, I can touch uh, and I can run ls. And that is definitely a read-write file systems. So all modifications are going to be saved. So if you are running your site systems as a dev environment, so switching to iSCSI is super efficient because you can quickly test update and modification. Something which is also really interesting is that you can use the DMF package manager from the distro. So to do that, you need to create the yum repo directory and a default um, environment for the OpenBMC RPM uh, repo that you have set up on your controller systems. So I'm currently copying and pasting this configuration, and I'm just going to start a very basic HTTP servers on the controller node. So that HTTP servers is going to serve all the RPMs which has been generating during OpenBMC compilation process from a specific directory. And then from there, I can issue a DNF make cache command, which is going to check the availability of the RPMs on the server side and validate that everything works properly. So you have seen that an HTTP GET command has been issued on the servers and that the metadata cache has been created. So now I can list all the installed package on my OpenBMC image and see how the image has been built and with what kind of features, the versioning, and all these kind of things. So we'll be seeing also that during the build process, there is more packages which have been built and processed by OpenBMC and which are not available on the image. And just to know them, just run the DNF list command. And and you are able just to install this package on your image because you have more storage capacity and you have read-write root file systems. So this is super efficient to run on-the-fly updates to your OpenBMC image. Let's wait for that command to finish. There is a ton of package, as you can see. And let's try to see if we can install one and validate the installation and removal of packages. It's amazing to see the number of packages which are available within OpenBMC. So this is bringing me to the idea that OpenBMC is a full operating system, and instead of considering it as a basic firmware image, so switching the management of that operating systems to traditional Linux tools might be way much more efficient than handling the image through static binary files, which are requiring long update processes and painful management when you have a very large fleet of servers. So the network is a little bit slow because I'm currently using the serial console from my system instead of using SSH. So let's try to install that small package, for example, the source code for the exe command. So I'm just issuing the DNF install exe source. It's asking me, hey, do you really want to install it? Yes. And it is processing the installation process. So we can check that it has been successfully installed by looking at the SRC, USR SRC directory, which has been created with the source tree, and we can remove the package. So making rolling back is very efficient too. So let's remove it. It's currently erasing the package, and we can validate that it has been removed by issuing an ls. The directory is gone, and the file system is here. We can see also that OpenBMC works by accessing to the OpenBMC console. The default login is there. So the connection is not private because I got a new certificate which has been issued by OpenBMC during the initial boot. So I can log into the OpenBMC console. It has recognized that this is an HP ProLiant Gen11 systems, but the good news, it's seeing it as being an RL300, which is my current system I'm running on. So now I want to refresh or update or scrap my test systems. So just to do that, you need to unconnect the iSCSI target. So to just reboot the machines, wait for the network configuration to hand over the iSCSI target image. So what's going on right now is a flush of the iSCSI target image from the memory to the file systems. So it is currently rebooting. I'm now rechecking the C route, the second root of trust. I'm going to stop the boot within U-boot environment. And if I'm getting back to the core DHCP web interface, so we'll be seeing that this system is probably considered as new, and it is considered as new. I can scrap it by clicking on the cross, and this is going to scrap it, and my environment is brand new. So this is a very convenient way to manage OpenBMC. It's also highly scalable. So what I'm thinking right now is to put this technology into top-of-rack switches and getting iSCSI directly served by management switches, and thinking about updating the BMC image. So either through a whole image refresh, which could be required in some cases, could be done just by updating the iSCSI target and removing all the client from the core DHCP infrastructures and just resetting them. And they will be just restarting with a fresh new installation. If this is just a small security update which needs to be done through package management, you just need to use DNF and you are good to go. And this is way much faster than the traditional process to manage the BMCs. Last but not least, if you want to run zero trust provisioning, so you just need to have U-boot working on the servers and getting the servers booting from the network. So you can ship your servers without any firmware image preloaded into it, and then retrieve that from a secure, well-known boot infrastructures. So this is opening doors to many different technology which are available on the OS side and not yet available on the firmware side. But I strongly believe that this is just some great things which might be happening to the IT industry. Thanks for your time. Thanks for watching and provide me feedbacks. Oh.